1. And another distance from our center of gravity to the existing rivet, we have here this as well. So since they are both located 40 mm above and below our x-axis, so we can just simply say this is our R2. And another one we have here, R3. However, this doesn't have y coordinates, so we can just simply neglect this one. So we need to solve for R1 and R2. So how to solve for R1 and R2? So since this follows somehow a triangle, so we can just simply make use of Pythagorean theorem by knowing the dimensions of its sides. This one and this one. And for R2, this one and this one as well. So now let us solve for R1 and R2. R1 is simply square root of, first we have here 80 plus the x sub g, that is simply 35.556, and our R1 is simply equal to 87.54 mm. Next, we need to solve for R2, and R2 is simply square root of 40 square plus, since we need to solve for this one, it is simply equal to this one 80 minus our x sub g in order for us to solve this one. So that gives us 80 minus 35.556 square, and R2 is equal to 59.79 mm. So we are already done with step 4, and right now we need to solve for the polar moment of inertia. And for the solution for the formula of our polar moment of inertia, that is simply summation of the area of the rivets times the distance square, and simply the rho here is our R1 and R2, which is from the center of gravity of our rivets to the location of our respective rivets. So right now we need to solve for the polar moment of inertia. So summation of first area of our rivets, so we have here 1/4 pi, and the diameter of our rivet is 10, and right now we need to multiply this by the summation of our rho. So we have here first R1, which is 87.54 square, and we all know that we have 2 R1. We have 2 R1, so we need to multiply this by 2. Next is for R2, that is simply 59.79 square, and we both have 2 R2, so we need to multiply this by 2. And we have here R3, which is simply equals to our x sub g, and that is 35.556 square. So for the polar moment of inertia, the total value for this one is simply 1,864,565 87.79 mm to the fourth. And right now, we need to solve for the value of P. Knowing that we are given the allowable shearing stress, we have already solved for the rho and as well as the polar moment of inertia. And the formula for that one is simply stress is equals to the torque times the rho for the critical rivet, the distance of the critical rivet from the centroid, all over the polar moment of inertia. We have already the value of our stress, the polar moment of inertia. We need to know the critical distance of our rivet from the centroid, and based on our values of rho, which is r sub 1 and r sub 2, the critical value here is the biggest one, which is larger value among the two, which is 87.54 mm. So for our rho here, which is the critical rivets, which is which has a distance from the center of gravity to the location of that rivet, is simply 87.54 mm. And right now we need to solve for the torque, and simply torque is the distance of our P times torque is simply the force times the distance, and that distance is simply perpendicular to the force that is present in our example. So here, since we both have P here, and we also know that there is a distance here of 120 and 100, I can just simply say that our torque is equal to, again, torque is force times distance, and we have here 2p, and distance from 120 and 100 from the x-axis respectively. So we have p times 120 plus p times 100, so that gives us 220p. So right now we can now solve for the value of p using this formula. So shear stress times is equals to torque times the rho all over the polar moment of inertia, and our allowable shearing stress is 70 MPa, and for the torque, that is 220p times our critical distance of the rivet from the center of gravity, which is 87.54, and our polar moment of inertia, which is 1,864,565.79. Then our P is simply equal to 6,777.14 Newton. All you need to do is to follow the steps so that you can solve for the correct value of our P. And you need to take note that in this formula, the distances here is from the centroid of the polygon to the axis it is being reckoned. However, the distance when you solve for the polar moment of inertia is from the rivet to the location of your center of gravity. And you need to take note also that it should be multiplied by how frequent, for example, R1 is present, R2 is present in your diagram or in your figure. So for this example, the answer is 6,777.14 Newton.